waiting some minutes to more participants, some assistants for the attendance. So let's start in 3 more minutes, please. Okay, we are going to start now in order to respect the time of the assistants. So then let me introduce to the conference for this morning. The title is Multiferroic Device and System Materials, Sensors and Actuators. This talk will be given by Professor, let me check it here to give the complete information, by Professor Chung-Min Leung, and he is an assistant professor in the School of Mechanical Engineering and Automation at Harbin Institute of Technology, Shenzhen, with a research interest in multiferroic materials, condition monitoring, sensors, energy harvesting, and converter applications. He earned his Bachelor in Engineering and PhD degree in Electrical Engineering at the Hong Kong Polytechnic University before joining Harbin Institute of Technology, Shenzhen. He served as a research scientist and postdoc fellow at Virginia Tech and at Stony Brook University. He has co-authored nearly 30 peer-reviewed papers in the research field of sensors. Most of them are in AEC, Applied Materials and Interfaces, Applied Physics Letters, etc. He's also a reviewer for many academic journals, such as the Journal of Material Science, Journal of American Ceramic Society, and so on. So let's thank to Professor Leung for his talk, and please.
Okay, thank you. Thank you so much. So can you see my PowerPoint?
Yes, yes, we can see.
Okay, okay. Let's start today's presentation. So as Professor said, that's my topic is multiferroic device and system, and this is the outline of my presentation today. Firstly, I will talk about a little bit about my background. So because maybe somebody wants to know much more about me, and then I will talk about today's topics. Firstly, I will talk. Uh, talk about the multiferroic effect and material. In here, I will little bit give a brief introduction of the multiferroic effect. What is it? How to measure the multiferroic, or we can call ME effect, and what is the thickness ratio relationship between each of the material and then also the bonding layer. Then I will talk about how to convert this kind of material to be the sensors. The first one is the AC magnetic field sensor, DC magnetic field sensor, and also the circuit. How can we build a circuit for the detection of the ME sensor? What is the noise in what's level of the noise in our ME sensor? And also what is the any other interference or influence between the radiation and the thermal property? Then I will talk about how to convert these magnetic field sensors to the AC current or DC current sensors. After I taught the topic about the sensors, I will talk about how to use this kind of materials to be the energy harvester. In here, I will mainly focusing talking about the magnetic energy harvester. Yeah, there are two types of it. One is called bilayer, and other type we call the magnet cantilever. Then I will talk another topic which I have done in the US on is called gyrator, magnetoelectric gyrator. So I will little bit give a little introduction of what is the gyrator and what is the important measurement properties of the IV-VI conversion and also the power efficiency and what is the limitation of the ME gyrator which I have done right now. And then I will say about the improvement. How can we improve the ME gyrator in the recent year? Then in the final part, I will talk about another application which I have used this kind of the sensor, actuator, or harvester to do another application on the power system, railway system, and some kind of self-sustainable current meter. So let me a short introduction of my background. I graduated in the Hong Kong Polytechnic University. Before I joined to the Harvard Institute of Technology, I was a research scientist and also the postdoc fellow in the Virginia Tech and Stony Brook University in US. Now, beside the sensors, because I have hybrid background, so I have some research on the material and also some research on the sensor and actuator. So I include all of the research publication. I have more than 70 SCI journal paper, and I got 21 H index in the Google Scholar, and I also the advisor board in the Journal of Applied Physics journal. And as I said that before, I have two parts in my research interest. The first one is material. I'm in. Okay, sorry. Yeah, I favorite in research in metastructive, piezoelectric, and magnetoelectric material, and then I also favorite in fabricate some metal sensors and actuator, condition monitoring system, and energy harvester, and so on. So now I have PI in many Chinese government-supported research projects. Is granted over 3.5 million dollars in R&D. In US, I have joined many research projects funded by US government like US Defense, US Department of Energy, and so on. And in Hong Kong, I have also had many industrial research cooperation projects, such as some MTRE is a big company of the railway company in Hong Kong, and also the CLP. CLP is the biggest power system company or power delivery company in Hong Kong. So let me give a introduction of the multiferroic effect and material. So what is the multiferroic effect or ME effect? And in here, we can divide into two parts or divide into two effects. One we call the intrinsic ME effect, and other type we call extrinsic ME effect. What is the difference of this? For the intrinsic ME effect, we can see in this diagram that we can find that for the magnetic, if we apply the magnetic field, and then the material can be direct convert the energy, magnetic energy, to the electric E field. But for the extrinsic ME effect, there are two parts of it. The first part is we need to convert the magnetic field energy to the mechanical energy, and then we use this kind of converted mechanical energy to the electrical energy. So this is the difference between the intrinsic and extrinsic ME effect. So in here, we will mainly focusing talking about the extrinsic ME effect, because the extrinsic ME effect, the output voltage or the ME effect is much higher than the intrinsic ME effect. So that's why we have received a much more application on it. So in the below diagram, we can hear it is much more easy for us to understand what is the extrinsic ME effect. We can have two kinds of material. One is called magnetoelectric material. This kind of material, when we apply the magnetic field on the material, we can result have the mechanical strain or stress. And then another material we can call piezoelectric material. In this animation, we can find that if we apply some kind of stress and force, the electrical signal or electrical output will become out. So we combine this magnetoelectric and piezoelectric material, and then have a result of the magnetoelectric composites. That means when we apply the magnetic field on the material, we can have the electrical voltage or electrical charge output of it. So this one we can call, when we apply the magnetic field and we still have the electrical voltage, we can call direct effect. Also, it's very easy for us to understand then what is the converse ME effect. That means when we apply the electrical voltage, we will result have the metallization or magnetic field will come out from the material. So this is another very important measurement for the ME material, I mean the extrinsic ME material. So in here we take one kind of for an example, one combination for the example, we use the table D for the magnetoelectric material and PZT for the piezoelectric material. So it is three diagram of it is very important. The first one, we can find that when we apply different kinds of bias on the material, we will result have the different kinds of the electrical voltage output. So, and the second one we can find that is talking about the linear relationship of it, because we want to use this kind of material to fabricate for a sensors. The linear relationship is very important of it. And then the third one is the frequency response. So if in the low frequency region, we can use this kind of material to fabricate as a sensor. And for the resonance, we can use this for the make a transducer of it. So this is the thickness ratio relationship of our material. So in here, there is some equation of it for the calculation. For this, for our material, we can find that for the long resonance and resonance region, there are different, different optimization thickness ratio. In here, you can find that for the best one is about 0.5 in non-resonant region. But for the resonance part, you can find that is 0.3 or 0.4. So you can find that for different application or different material, we need to consider different thickness ratio when we want to be a sensor or actuator. And other thing is because we bond these two materials together to form a extrinsic ME composite. So the bonding adhesive layer is very important. In here, we did many research on it, and we found that the epoxy adhesive is much, if we want have a very good ME output, the main problem is come from the epoxy adhesive. So we try many epoxies and also the thickness of the bonding layer and also the pressure of when we bond the two kind of material. We find that if the modulus of the epoxy adhesive is much more, is it to be same with the piezoelectric material. You can think that if the epoxy is very hard, the material will be rigid, and then it is very difficult for it to elongate it. So we can find it from these two diagrams for the yarn modulus and the thickness of it. So it is a very short summary about the material part. And in here, we try different kinds of materials. So MagGas is one of the very good magnetoelectric material, and PMMPD is another piezoelectric material. So for different kinds of material, we have different long resonance or resonant output voltage. For up to now, we can find that for the MAN-DOT and PMMPD MagGas material, we can get the highest 61.5 voltage per centimeter Ostar for the non-resonant region. But for the resonant, we need to change another kind of material, let's say aluminum nitride and the MagGas, and then we can result in about 200,000 voltage per centimeter per Ostar. So it is the talking about the material part. If you have interest, you can find the research paper which I have. It is a review paper talking about all of the ME Composite material and the sensor you can find. If you have interest, you can read it. And after we fabricate the material, the next part is we want to convert it to be a sensor. So it is the AC magnetic field sensor, which we use the ME material. In here, we use two for the magnetoelectric material, we use the MagGas material, and for the piezoelectric material, we use the PMMPT fiber. For the piezoelectric material, so in here we can talk a few things. The first thing is at the very beginning, for the most engineer or the researcher, we think that if we want to fabricate a very good sensors, the output voltage should be as high as possible. But later on, we find that even though we got a very high ME output voltage, but the noise of the sensor will also be increased. So we have another research on or other combination of the ME material to be a magnetic field sensors. So I will talk it. I will present it in the next part. So beside the AC magnetic field, we also use this the zinc material to be the DC magnetic field sensors. And here we use the zinc material, and then in here we make a surge coil in here and provide the AC current in here, and then that means there is some AC magnetic field provided by the surge coil. And then we use this kind of region to detect the DC magnetic field for the external one. So we can find that there's very linear relationship between the DC magnetic field and the output voltage. Besides, we only use the material to be to detect the AC magnetic field. We also fabricate a circuit for it, because if we want to detect a lower magnetic field in lower frequency regions, the circuit is the charge meter is necessary for it. As we know before, if we the magnetic field sensor or even though another kind of sensor, the output voltage will be affected by the connected cable. You know that, as we know that if we want to measure the output voltage of the sensor, is maybe very much of loss if we use a very long cable. But if we measure the output signal by the charge from the sensor, we can eliminate the output loss of this. So in here, we fabricate a circuit to convert the output voltage to the charge. So after we fabricate this circuit, you can find that we can measure a very low frequency region and as low magnetic field. And then we can find in here with the detected frequency as low as 3.1 millihertz right now. So in the beginning, we talked about the ME sensor. We not only consider the output voltage, but we also need to consider the noise in the ME sensor. For the noise, there are two kinds of two main noise in the ME sensor. The first one is dielectric loss, and the second one is the DC resistance loss. And then we combine it to these two kinds of noise. We have the total noise in here. So we can look at this diagram. We have the purple color is the dielectric loss noise, and the blue color curve is the DC resistance loss. And then this is the simulation, and this is the measurement result, and then two comes together, and then in here this is the output charge of the ME sensor, and this is the size of our ME sensor. So for this kind equivalent magnetic noise for each sensor, if the curve this one as the better sensitivity, or we can say yes, a better performance of it. Another thing I want to talk about is the piezoelectric material. In our research, we try to improve the performance of our ME sensor. We can say magnetic sensor. So we try another diagram. We can find that there are different kind of loss, dielectric loss for the material. We try high loss, medium loss. Definitely, equivalent magnetic loss is the lowest one. So that means we can have a better detection performance of it. So you can find in for this diagram, if we choose a lower loss piezoelectric material, we can detect a lower magnetic field of it. So this is a 120 picotesla, but for the highest loss one, you can find it is only 12 nanotesla. And then we also test do some experiment on the temperature increments. So we can find that for the piezoelectric material, if we have a higher temperature, the dielectric constant will be higher. As a result, the ME output voltage will be higher. But for the equivalent magnetic noise, we can find that if we have a lower temperature, the loss noise will be higher. But if in higher temperature, you can find that the noise will be lower. So there is a trade-off of it, because in here we can find that if we have a higher temperature, the output will be higher, and then for this one is higher temperature, the noise will be lower. So this is the final result we can test to combine the noise and also the output charge of it. Because our ME sensor have a very the coil of our ME sensor is piezoelectric material, that means it will respond of the external vibration noise of it. So in traditional, we usually use the cancellation methods to cancel the external noise. But in here, I propose another kind of method is the internal vibration cancellation. So we can find that when we apply the magnetic field in the material, the magnetoelectric material will be divided into two parts. The first part is the wavelet will be elongation, and it will be condensed. So internal magnetic field on is one of the faculty of his magnetoelectric material will be elongated, and another will be condensed. So it is the different in different directions. So as a 100 for the electric material, and this is the result of this. If we directly use the ME sensor when we apply a big vibration noise in here, as a result, we can find that there are big vibration noise coming out from the sensor. But in here, we apply the same vibration in here, the result will be lower. This is the output result of the ME sensor. Okay, and this is the applied vibration. Okay, so we can find that if the ME sensor without the vibration cancellation, the output voltage will have some vibration noise. But in here, we can, in fact, we eliminate some vibration noise of it. And this is the summary of the ME magnetic field sensors. And then in the blue curve is the result of our ME sensor up to now. And this one is the squid. As all we know that the squid is a very good magnetic field sensors, but the price of the squid is very high. As we know that is about millions US dollar. And then for the first gate and automobile bump, we can find that for this three kind of the magnetic field sensor is have a better performance compared with our ME sensor. But for the price of these three kinds of the sensor is much higher than our ME sensor, because the fabrication price of our ME sensor is only about 100 US dollars. And compared with the similar fabrication price of the search coil, we have a very good or compatible performance detection performance of it. Okay. After we make the ME magnetic field sensor, and then the next step is we change it and then make it into the ME AC current sensor. In here, we use a very the university method, the right-hand give rule. When the current applied a line, and for the right-hand give rule, the magnetic field will be generated in the circular direction. So we use this kind of the simple Ampere's law of the it, and then and as a result, we detect the AC magnetic field, and then we can calculate best to the how much of the current applied on the current line. After we fabricate the first type of plane shift ME sensor, we find that the accuracy is not very good. So we capture some idea of the current transformer or a Hall effect sensor. We fabricate another type of the current sensor we call ring shift ME AC sensor. And then, as we all know, that it's much more easy to concentrate all of the magnetic field from the electrical AC current cable. In here, you can find that we use the same volume dimension of the reluctance coil, that means the search coil, and compare with our ring type electrical current sensor. The very important thing is in the low frequency region, we have a very flat detection and also the very high output sensitivity compared with the reluctance coil in the same one direction. And this is some kind of the result of the output voltage. We also have a very good in phase and also a very good shift without too much noise of the output scientific sine wave of it. After we fabricate the AC current sensor, and also we use this same ME material to make an energy harvester. So the first step, you just directly use the ME material to detect the output voltage or output power of the material. And then here is the output performance, which we can find it strongly depend on the different kind of resistance load of it. But in here, as we all know that in our home or in our power system, we usually use the 50 Hertz or 60 Hertz in the Europe. Okay, so in here we can find that the resonant frequency region is far away from the 50 Hertz or 60 Hertz. So for the next step, we try to use some tip mask adding on the PZT materials to make it much more to reduce the resonant frequency. So in this diagram, you can find that without the mask, we have the higher resonant frequency. So that's why we are difficult to harvest the energy in the power system or the electrical cable. So after we add the two magnet or four magnet, we can find that we reduce the working frequency of it, and then we can match our power system or electrical cable. So in US, we usually is 60 Hertz. So, but in China, as all we know, that is the 50 Hertz. So we can use this kind of method to tune the working frequency of it. So the next step, we can tune the working frequency, and then we also want to harvest much more energy from the AC current cable. So we fabricate another type of is we use the banding structure cantilever beams to make the piezoelectric material have a higher banding. So it is the result of this, and here we can find that we have the 125% enhancement if we use the banding structure of the ME material. So after we use the ME materials to do the energy harvester and also the magnetic field sensor, we use this kind of material to do a power conversion device we call the gyrator. For the gyrator is a linear passive two-port electrical element which proposed by the Telegram in 1948. So as we are the electrical guys, we know that there are four kinds of the linear element in the basic linear element. The first one is resistor, the other one is capacitor, and the third one is inductor, and the fourth one is the ideal in transformer. So for Telegram, he proposed that after this four linear element, the gyrator will be the fifth one. So what is the difference between the transformer and the gyrator? For the transformer, we all know that it is the voltage to voltage or the voltage to current conversion device. But for the gyrator, it is the current to voltage or voltage to current conversion fixtures. And other thing is the impedance conversion between the input port and output port. As we all know that the transformer is wound by the copper coil, so that means for the input and output part is also mainly is the inductance features. But for for the gyrator, the requirement is for the input part we may need the inductance, but for the output part we need the capacitance. So and for the ME and after in the 2000s year, our group find that we can use our ME material and wrap it for the surge coil or it, and all we know that for the coil it is the inductance features, but for the piezoelectric material it is the capacitance features. So we use this material to make the first gyrator of it. Before our proposed in the world, there are no one can make a passive gyrator. Just somebody makes the gyrator use the operational amplifier. So in US, I make this TFLD PZT ME gyrator, and then I try to measure the IVVI conversion performance of it. And for another one, I also measure the power efficiency, because as all we know that for the transformer, there are very high power efficiency, more than 99%. But so the first step, if we want to use the ME gyrator, we also need to test the output power and also the power efficiency between the input part and output part. So in here, unfortunately, in the first experiment, we can find that it's only about 30 or 40% between the conversion input part and output part, I mean the conversion ratio. So The next step we want to do is increase or enhance the power efficiency of it. So I tried many kinds of method and change the material. So I found that for the nickel ferrite, we can have a much higher power efficiency. We can find it is about 60% 60% of the power efficiency. But we have another problem when we use another kind of material. We can find that when we drive the generator in the very much higher power region, the power efficiency is decreased. So the first step I try to improve this, I try to solve this problem is choose another kind of the configuration features. For the original one, we use two metastructive material, and then we sandwich it for the one piezoelectric material. But we find that the problem is usually come from the metastructive material, so we try to use only one metastructive material and sandwich it by the two piezoelectric material to, and we watch the mechanical tamping on the metastructive material and make it have a higher power. It can make the higher power efficiency in the high power drive. So in here we can find that for the NPM and PMP type, okay, we can find that for the PMP type we have still remain a higher power efficiency if we drive in much more time. So the next step is we know that the problem is come from the metastructive material, so we have some research on this. So we try to add one ion, that is the material ions in the nickel zinc ferrite. So we can find that if we have add about 8% of the lithium in the nickel zinc ferrite, the power efficiency can remain constant. We can find that the blue one is a power efficiency when we driving in the high power region, the power efficiency can remain about 80%. But for the original one, if we drive in the 40 watts per inch, the power density, the power efficiency will be reduced to about 60%. Okay. So there's some other improvement. So let me give a short summary of the ME generator. We tried different types of materials, say TFLD, nickel zinc ferrite, or ETM dot nickel zinc ferrite. And finally, we find that for the if we replace the nickel zinc ferrite by the matte material, we can get the highest power conversion efficiency about 95%. Even though we drive it in a very high power region, this can still remain the 90% of the power efficiency of it. So after we talk about the ME generator for the sensor, let's also talk about the other application of the ME material. At the very beginning, I fabricated a ME sensor of this, which can detect the AC current. So this is the LV cable switch gear in the CLP. CLP is the power system company. Okay, and then we go to the company to test our sensors, and then for the original one, we can firstly look in the left-hand corner diagram. For the original switchboard, we can find that there are many. The white one is the CT. For the original one, the power company used the CT the current transformer to measure the AC current. But we can find that for the CT is very bulky and very big. For this cable, right? For the blue one, we can find that there are low CT on it because there are low gap or low place for the CT to clamp the cable. So the power company think that our ME sensor is very small. So we try to use our ME sensor to install it in some cable which may not have in the space of it. So here is the result of it. Here is the 28-day loading pattern, and then we can find that even though our ME sensor not only measure the loading of the the cable, but also we can measure some sparking in the operation of it. There are another application for the traction system in Hong Kong, MTR. This is the railway company of it. In Hong Kong, there are for the train there are 12 carbons, but only 4 carbons have the motor drive. And then the engineer in the railway company told us that there are sometimes when they operate the trains, maybe the motor of the train will be shut down. So even they cannot find any kind of methods to detect the problem of the shutdown problem of the motor. So they asked us to help them to install some ME sensor in the current drive cable and use the wireless power transmitter to transmit the opposite load back to the driver carbon. So it is the result of it, and we can find that we can detect the total harmonic distortion and also some error and also some condition monitoring application. And we also try to use this kind of sensor to help the Singapore MTR system to measure the sparking of it. This is the string and the current sparking result of it. And this is another application of our ME sensor, which I have done in Hong Kong. So in here is we call the self-sustainable current meter, which integrated with the energy harvester. So that means that this current meter can measure the current and also can harvest the energy from the current cable to drive the wireless power transmitter. So in here, we can find that we use a passive current sensor and to measure the current, and also use this kind of it to harvest the energy. And this energy will provide the energy to the microprocessor. And for the microprocessor, there will connect 2 parts. The first one is the e-paper, and other one is the wireless transmitter. And for this one, it is not very innovative thing. It's just wireless receiver and receive the wireless signal and connected to the computer. And for the e-paper, all we know that there are one critical features of this, because for the e-paper, if it just wants to display the word for the e-paper, it will not require any energy. The e-paper only require the energy when it's refreshed. Okay. Okay, this is some demonstration and for the video of our self-sustainable current meter. In here, the left-hand side is the diagram of the charging time, because we install a supercap in the energy storage, and then for the current, when we apply the current measurement circuit will try to store the energy to the capacitor, and then when the capacitor is fully charged, and then we will send the energies to the e-paper and the wireless transmitter and give the measurement and the detection for the output. And then for here, it is the wireless receiver, that means the computer size, and this is our ME sensor and energy harvester of it. This is just a standard current meter of it, and this is the e-paper and energy harvesting circuit is here. So for the video at the very beginning, we can find that for the current meter, this is only about 0 amperes. So that's why for the e-paper is up here 0 amperes. But as so we can find that when we turn on the AC current, the e-paper will also display something, because the e-paper is just requires the energy when it's refreshed. So let us start the video. So when we start the current, it's about 5 amperes. Now it's 5 amperes, so the energy is charging, okay? And then if it's fully have a charge on the capacitor, we can find that the e-paper will be refreshed. And then after e-paper refresh, the energy will still charge again in here. And then it refresh again, and then we can try to enhance the current, input current of it, and then we can find that the reflection time will be faster. So I'll just stop the video and then let me. Okay, so after the energy this demonstration of the energy harvester, let us talk about some recent research which I have been done. So as with the very beginning, we fabricate some ME sensor of it, and then for the ME sensor, after we fabricate the ME sensor, we try to use this kind of the ME sensor to detect the eddy current testing from the material. So we can imagine that there is some material and then there are some crack on the material, and we use the eddy current method. We know that for the wave cable, when we apply some magnetic field on the material, there is some eddy current generated on the material if it is the conductive or metal material. So we use this kind of method to detect the eddy current changing by the crack. So this is the combination of it. For the red one is the single coil which we the commercial product, and you can find that for the single coil, it can only be detect the metal material, but it is very difficult to detect the crack of it. But if we use our ME sensor, we can find that even though we can detect the conductive material, but we also can detect the crack in here. And so this is another kind of measurement result of it. After at the very beginning, I already told us that we have the ring shift current sensor, which I have published in the few years ago. After that, I found that there's nobody to do this kind of measurement. So I took it back again and tried to do it much better. And at the beginning, our AC current, ring shift AC current sensor is only about 10 milliamperes for the lower sensitivity. That means I only can measure the 10 milliamperes of the input current. But after my trying to another kind of method, we can find that we can detect the 0.3 milliamperes right now. So it is much higher improvement compared to the original one of the AC current ME sensor. And this is the final part which I have been done which I've done in recent. It's called very low frequency magnetoelectric antenna. For the antenna, as we all know that if we want to have a very far or in the underwater or in the sea to do the transmission, the low frequency is the only way to do it. And then we can find that for the very low frequency bandwidth, in the traditional one, this is the one antenna which have been fabricated or built in Japan. For the very low frequency band is about 10 kilohertz. You can find that the highest of the antennas is about 400 meter high. But for our ME sensor, we can find that if it just wants to work in the same frequency bandwidth, our ME sensor is only about 12 centimeter, and then we can have a similar performance of it. And then this is some result of our ME single ME laminate of the ME antenna, and then we just actually we only try this in the laboratory part, so we just measure in the short distance. But compared to the result, we have a good. We believe that in the future we can have a better performance, and we will also try to measure in the outside or in the countryside environment to test the wireless transfer distance of it. Okay. That's all of my presentation. Okay. Thank you very much.
Thank you very much, Professor Leung. Now it's time for questions. So anyone from the audience wants to ask something? Okay, if not, I like to make you a question.
Okay.
I am interested in the sensors. Until I see you work in the noise reduction and talking about the range of the sensors, but what are the challenges now? Is the miniaturization, try to reduce even more the noise, or to increase the range of operation of these sensors? What do you think is the challenges now?
Okay, for the challenge now, for our sensor, actually we can have a very low noise right now. But for the frequency region, we can actually we just can measure about 200 kilohertz right now. But as we all know that if we some of the switchboard power supply or another some kind of application is already 1 megahertz or even higher. So it is the most challenging right now. We also do have some research working on the ME film. It can be measured higher working frequency, but honestly, the output sensitivity compared with the original one is not very as good as the original. So we are only trying by our effort in here.
Okay, thank you very much. Anyone else from the audience want to ask something? We are almost on the time, so maybe one question more is possible to do it. Okay, maybe I make the last question then. Talking about the girators, I never heard about that. So interesting that it's a new device, but what do you think that is the main application for these girators? Is used to in order to convert, and also how do you determine the conversion ratio for these girators?
You mean the ME generator, the one which can convert the IV and VI conversion one? Okay. The one actually this research project is funded by the U.S. Defense. So some very secret application I cannot tell you that, but for the general one I can tell you that we can use, as we all know that for the LED light we usually use the current method for the driving, but for the original one we usually use the voltage transformers. That means it is very little difficult for the driving or tune the light brightness. So we use we have one application we can say is use the for the LED driving, use the voltage mode to convert the current mode to drive the LED. But as I said, that for the another application, I cannot tell you that because it is some US defense project, which I have already signed the contract.
That's fine. That's fine. Thank you. Thank you very much. Then maybe this is all for this talk. We are really thank you. We really want to thank you for your time. I know that now is even 12 at the night for you, so we really appreciate your effort and that you substitute for my friend, my colleague friend, Ron Wu. So thank you very much. And we will send you the diploma for this event. Due to the change, we don't have it now, but we will send you to you. So thank you very much for your time and effort for doing this work for us and this presentation for us. Let's thank to Professor Leung. Thank you very much.
Okay, thank you so much. I'm also very honest to have do the presentation in here because I only do the presentation in the US, China, or Hong Kong. I seldom do the presentation in Europe or even the Mexico in your country, and it's great honors for me and a very good chance for me to do a presentation in different countries.
Oh, thank you very much. So maybe we see you next time.
Yes,
so,
see you.
Thank you very much. And for the attendance, we would like to invite you to continue in the next events for this seminar. So thank you very much.
Okay, see you. See you.
Good evening.